Hi guys, can I get a sound check?
I can hear you.
Thanks. Hi.
Hello.
Okay, guys, let's get this thing kicked off. So every semester, when I teach this class, also like do some extracurricular activities, or just for fun, and give you guys a taste of I don't know, something I've worked on, learned, and so this semester, I guess it's going to be talking about entrepreneurship, and I'm going to sort of start by, I'm not sure how to do it, so I'll sort of do it anecdotally, because I'll tell you why. Maybe more from my experiences. So I wanted to become, and feel free to tell me, by the way, or email me or whatever. If this isn't, it's not like what you guys were looking for, I can get more specific. But, um, I figure like if you want to learn about various like specific things, there's like good books to read, et cetera. I can be more helpful with experiences as an engineer who started the business or was involved as an engineer in different types of businesses and kind of was paying attention. I'm hoping that's what I'll be talking to you guys about. So for some reason, I got it in my head since I was like 18 or 19 that I was going to do a startup someday. Okay. Don't ask me why. It's got this crazy idea in my head. So it kind of set my direction in life. I went to grad school, honestly, primarily because I thought that it would help me start a business. It was probably not the best reason to go to grad school, but um, but the nice thing was I actually learned that was the whole grad school experience itself, as painful as it was, it has its own values. I can see that now, years away. So I went to there, then I went and specifically worked on startups to try to understand how startups work so I could build my own. So I worked, right after grad school, I spent a year and a half in JPL just because I thought it was important. I got my PhD. I thought it was important to go work at a research institution just to kind of give myself some legitimacy. It just happened that I ended up working on this really cool area that sort of I stuck with. And I joined, a couple of startups, and I was paying like a lot of attention to what the company was doing in both of those startups, just because I knew I wanted to start my own. And then, I started my own company with some friends. And then, like I mentioned, we sold it in 2018. So why do I mention that to you guys? It's because I'm not like a business person. I'm a technical person who built a business, and I'm a technical person who worked for businesses, et cetera. And that's important because I'm talking to a room full of engineers who might want to build their own companies. It's not, you guys aren't a room full of MBA students or something like that. You're all engineers. And why is that important? It's because this is the first thing I wanted to talk about is when you're an engineer or a non-business engineer, I'm just going to talk about engineer, right? When you're an engineer and you're interested in business, it's easy to get confused. So that's the first thing I want to talk about is the confusion and like what you might experience. So like I mentioned, since I was 18 or 19, I was interested in business. So start reading business books, right? Trying to find out about business, trying to talk to different people. Like I mentioned, I was reading Wall Street Journal, whatever, all these kind of business things, reading about business stuff. So you're looking at all this stuff, and there's a few things that makes it confusing. One of them is that business is actually a pretty gigantic field. Okay. When you're talking about business, there could be, it could be talking about finance. You could be talking about marketing. You could be talking about sales, which coincidentally is not the same thing as marketing. Those are all mentioned, sales and marketing at the same time. They're very different. You could be talking about general management, like, managing employees or human resources. You could be talking about business law. So there's a lot of stuff that is, when I say business, it's it's a huge thing, right? And on top of that, you have different even types of business, right? I worked after we got bought by a Fortune 500 company, and which is a public company, billion, I don't know what the valuation is, 15, $16 billion. And always had this thought when we were, when we started our own company, we're just doing stuff, and you know, we sold the company when we were about 50 people. Okay, and always thought I was missing something somehow, because you know, you're reading in the literature about this thing, and you should structure your company this, and they're talking about different things, and we aren't really doing any of that. We're just we're a very flat organization, so we're not like worrying about, you know, managing employees in certain structured ways, and we are I don't know, like we didn't have a budget. I just sort of like, we made things up as we went because we were growing quickly and we just didn't know what our budget would look like next year. We're just constantly growing. It wasn't like we were on a steady path. So I always felt like an inferiority complex, like, man, we should be doing all this stuff to manage our business. When I went to this Fortune 500 business after they bought us, I saw all those things in action. It's actually a very well managed company for a large company, for a large public company. And I realized all those things that I thought we were missing for a reason. It was because they were not useful to a company our size. Okay, so that's like the number one thing. You got to realize business is a big field. Don't get wrapped around the axle with, you know, there's a lot of information on, you know, lots of books, lots of great books, but you somehow you got to figure out what will apply to a small enterprise, which is by definition what you'll be starting. So that's one. The second thing is that business, it's not like engineering. Okay, so it's like if you get 10 experienced chip designers, analog designers, and you ask them, you know, here's an amp I want to design. Why should I put it together? 10 out of 10 times you're going to get more or less the same answer. You know, it might have a few biasing techniques here and there. And you will all look at it and you'll look at each other's solution and come to a definitive agreement about which solution has more noise or more current or bigger area. It's engineering. There's like variations in engineering. There's an art in engineering, true, but not to the extent that they're in business. So in business, there's like a million different approaches to do the same thing. So you might talk to one experienced business guy, you might get an answer. You might talk to another experienced business guy, you might get a very different answer. If they get together and they're good business people, they'll understand each other's point of view, but they may not necessarily agree about what the best path is moving forward. Okay, so it's just not that scientific in my experience. Okay, at least certain aspects of business are not that scientific. Okay, so those are two confusing reasons. The third thing is, because we're engineers, because we love engineering, that's why you've started a business. Even if you think you hate engineering, you love engineering, believe me, and that'll become more clear to you as you go on your path. Your mindset always reverts to engineering in the sense that you will tend to make engineering decisions drive business decisions rather than the other way around. Okay? If a true business person is just thinking purely in terms of profit, loss, cash flow, stock price, employee compensation, blah, blah, blah. You are, even if you try to just keep your head in that game, you will constantly drift to, hey, is the product, how awesome is the product? Is this going to have, you know, is this going to beat the other people, or we need to do this to get a better quality product? or get it to market faster, you're always going to be tempted to go back to have engineering drive the business aspects. And that could be good or bad, but it happens. So those are like what makes things to keep in mind, because we're not business people, and it seems like sort of this black box, but those all tend to confuse us. Okay, and so I'll stop there because we probably don't have a lot of time. Just wanted to start there with like the problem definition. We're engineers that are doing business. We're not business people that have an engineering company. Maybe, you know, there might be exceptional cases. I don't know, like your mom or your dad or are business people, and you know, you were seeing how they operated from the get-go or something like that. Maybe you have business in you already. Maybe you already have that knowledge. You know, I didn't. My dad is, both my mom and dad are like teachers, educators and stuff. So I just had to learn my own. So I'll try to like sort of follow up on that in the next lecture, etc. What was this ramblings? Was it interesting to begin with? Does it go in the right direction? Any
interesting.
Yeah, I appreciated that.
Sure. Okay. And then as we'll go, hopefully I'll get, you know, by week 3 or 4, maybe we'll get to something a little bit more concrete as we sort of walk through this maze. Okay. So I'll leave it there, guys. And now we're going to go back to technical activities. So last lecture, and I thought it was important. We watched a bunch of videos to get you guys to kind of visualize when we're building these silicon chips, what does it look like? Like I mentioned, you know, we had this process where we start with a wafer of silicon that's, you know, now it's almost all 12 inches in diameter and about 1 millimeter thick, okay? And all the stuff, all that happens in that piece of silicon is happening in the very top layer, the very top 5 micrometer, 10 micrometer of that silicon. The rest of it is just mechanical support for that top layer. That's all you have it there for. The other thing is this process sort of fundamentally is called a planar process. Why planar? Because it's happening in a plane. All the transistors are sitting in that top plane. You don't have transistors sitting on top of each other somehow. All the active devices, transistors, diodes, those kind of things, they're all on a plane. Okay, that's, well, I think that's an important thing to think about. So those aren't like, they're just sort of sitting next to each other on this plane. Now, the stuff that's above those transistors, which are the metal interconnection layers, et cetera, that connect those transistors together, they're more are in multi-planes. So you have like a metal line, another metal layer, another metal layer, another metal layer. They're not going to be all the metal layers are not sitting on a single plane. They're like multiple planes stacked on top of each other. It's still, you know, a few microns from the surface, but so that's what it's called, a planar process. Okay. So when you look at it, when you look at this thing, at your silicon diode from the top down, which in this drawing, remember this is a cross-sectional drawing here, as if we cut, this looks like we cut the wafer and looking at it edgewise. So this would be as if we're looking into the wafer. When we look at that, if, you know, if you're in an older process, you'll see a sea of transistors okay, sitting next to each other in different ways. And then you'll see like metal lines crisscrossing and connecting everything together. Okay, so the second thing to think about or understand is that, or at least the way I look at it, there's sort of broadly speaking, there is two parts to this. One of them is sort of the active silicon, not sort of the active, it is the silicon, okay? So the silicon all is below the surface is the way to think about it, okay? So all the silicon is ion, things like you're adjusting, you're doping the silicon. I don't know if you guys are familiar with doping and stuff, but you start with the silicon and you're adjusting its donor acceptor concentration, stuff like that. You're not building anything on, you're not depositing anything on top, okay? You're sort of, what you're doing is you're putting ions in the silicon itself to get N regions and P regions and N plus regions and P plus regions, so on. But you're not putting anything on. So that's everything underneath the surface, I guess maybe by definition. Anything above the surface, almost everything above the surface is put there by deposition. So you actually deposit a whole layer of aluminum or copper and pattern it, but you actually have to deposit it on, and you pattern it, and then you put a layer of dielectric above it to isolate it from the next layer of metal, et cetera, et cetera, et cetera. So it's kind of like almost like divided in half. So this is like the surface, everything below is silicon, everything above almost is not silicon. I mean, the gates are polysilicon, so that's an exception. So maybe I'm being over general, but everything there is like basically metal interconnections and so on. Okay, so let's talk a little bit more about this process. Okay, so maybe it's just sort of saying the same things. I was just, whoops, sorry guys, let me take a look at my notes here. So confusing. Excuse me guys for a second, I'll get a look at the right. Notes. Okay, I got the right thing now. Fine. So what I want to say about this. So I think I already already said it. So again, everything above here is sort of dielectric and metal. Everything below is silicon. Now let's look at some particular things here. I talked about it last time, but let's look at it a little bit more detail. So the first thing, so this guy, so again, this is a cross section. So this is as if you cut the wafer and look at it, you're looking at it edge sides. So this means that this substrate is sitting on is actually like 750 microns thick, and the rest of everything is like 10 microns thick. Okay, so all of this is P plus. Okay, so that means your wafer, so I'm not going to draw it here, but that's just to help you guys visualize. So when it says, you know, this is a substrate, it's actually, this is pretty thick. Okay, it extends all the way down. So it's this P plus material, okay? And most silicon wafers are P plus, okay? All right, so the next thing that, why is it P plus, okay? So for, this is a little slightly deceiving, but the reason for it being P plus is because you want to have low resistance. So P plus means that the silicon is heavily doped with acceptors. So it probably means boron, which is sort of a popular acceptor or P-type material. So, and once something is heavily doped, like if it's P plus means it's a lot, you know, doped a lot. and N plus means it's doped a lot with donors or be phosphorus or arsenic. It means it's has low resistance, okay, because it has more free carriers. The number of free carriers is a certain number of dopants. So the more dopants you have, the low resistance you have. And you want that substrate to be low resistance because you want to basically make sure it's the same substrate potential everywhere. Okay, so when you have something that's P plus, okay, what you do is you ground it, and you have a nice, because it's P plus, you have a nice ground underneath all your transistors. Okay, remember that this chip could be 10 centimeter on a side, 20 centimeter on a side. So it's really nice to have a good low resistance ground where, underneath all your transistors. Okay, so that's why it's P plus. Now, the next step that people typically do, it's not done all the time, but around 99% of the time, they basically change the doping concentration on the very top, and this is called the epitaxial layer. I think epi means surface or something in Greek or Latin. Anyway, I don't know. Epitaxial layer it's called. And so what they do is they reduce the P doping concentration, so it becomes a P minus. So the epitaxial layer is P minus, means that it's slightly P, not a whole lot. And the reason for that is, so use this for conduction. The nice thing about having a P that's not so highly doped is that it's easier then to put your NMOS transistors on there. This is showing a P well underneath your NMOS transistors, but you don't always get that. So most of the time, your N-type transistors are sitting right on, whoops, shouldn't have done that, or sitting right on top of your epitaxial layer. Okay, so, and then you put in this N plus. This is not the sequence you do it in. I'm just sort of describing what are the different components here. So you have, these are your source and drain for your NMOS transistors. Again, those are N plus, which means highly doped with, so N is donors. Those are, again, tend to be phosphorus or arsenic is what they dope it with to get this heavy concentration of electrons. You have a gate dielectric, which is silicon dioxide. Okay, and then you have an actual polysilicon gate. So, this is your NMOSFET schematic drawing. You have your source, you have your drain, and you have your gate. So this gate is polysilicon sitting above your substrate, and the source and drain are these N plus sort of doped areas in the silicon. Okay, so simultaneously then you're also building up P transistors because it's a complementary MOS process. You have both N type and P type. Oops. Transistors. Okay, guys, by the way, is there anybody in the class who hasn't seen at least N and P type MOS transistors? We're going to go over them, but I just want to know, it's just, hopefully it's not completely new. Anybody? Don't be shy. Speak up. No? So when I say N-type, P-type MOS transistors, everybody gets it?
Yeah.
Okay, awesome. Thank you. All right. Well, we're going to go over them a little bit, but okay, I just want to see where we are. Okay, so the P-type transistors have P plus for their source and drains, which means they have a lot of holes. Then they have polysilicon gates like NMOS. And then you basically start contacting to these areas with different types of contacts. Okay. So this presumably is the first layer of metal, which is called metal 1, M1. Always called metal 1. The one closest to the substrate is always called metal 1. Okay. And it connects to, so the metal 1 connects to the sources, the drains, the gates. And for whatever reason, they call this contact layer, they call it contact, which makes sense. Okay, except that when you have another layer of metal, so this would be metal 2, notice there's a dielectric layer between insulating, there's a layer of silicon dioxide insulating the metal 2 from metal 1, except where there's a contact accidentally, not accidentally, a contact intentionally put in to connect metal 2 to metal 1. Now, the weird thing is anything other than these first set of contacts, they're all called vias. So anytime you have a contact between metal lines, they're called vias. Anytime you have a contact between a metal line and either diffusion or polysilicon, it's called a contact, and it all happens in the lowest layer of metal. Okay. Okay, I think that was what I wanted to talk about there. Okay, so we're gonna build up some details about this, but you guys saw in the video, the videos, that these wafers start on one end of this factory and they go through a series of steps and they get carried with these robotic carriers with this railing system. So what happens is they, something happens to the wafer, set of wafers. Usually they, almost all the time, they either work with 12 wafers at a time or 24 wafers at a time. I don't know why it's not 10 and 20 or anything. 12 wafers or 24 wafers. And that's called a lot. That's called a wafer lot. Depending on which foundry you're in, it could mean a lot could be 12 wafers or 24 wafers. And those wafers in that lot are all sort of traveling together, and the same thing happens to all of them. So those guys are all moving from station to station and getting worked on from station to station. By getting worked on, it's all happening automatically by these machines, and they're doing these steps to these lots, and then other lots are moving through. So essentially, at a very high level, these are the steps that kind of happen to these wafers at a very high level. The first steps happen just to the silicon itself. Remember when I was saying that when you're below the silicon sort of layer, below the silicon surface, it all has to do with implantations, basically adjusting the doping of the silicon itself. Okay, so you have these implantations, which is a way of adjusting the doping concentrations, etc. One thing, by the way, I didn't mention here, or I should have been better here. No, here's better. So because of different reasons, which we'll might go into, is you have this NMOS and a PMOS in the same substrate. They are isolated from each other by the N well of the PMOS, but for reasons that we probably won't get into, you'd like additional isolation. So what do? So what you do is you actually etch the silicon and you fill between the transistors, and you fill that with some dielectric typically silicon dioxide, okay? And so that is an isolation between the transistors. So that also happens at this top part. So you actually etch the silicon, and that isolation is called a trench. And so you etch it, you fill it with some dielectric, probably silicon dioxide, but it could be something else. Okay, so this is all stuff that's happening, that's putting the, you know, the sources, so all this stuff, which is the first step, is the isolation, sources and drains of the transistors, substrate contacts. So that's kind of what happens here. The next step is you deposit and pattern the polysilicon layer. The polysilicon is the gate of your transistor, okay? So this is your gate. Okay, and then we'll see why this is the case. You will, after you put in the gate, you will adjust the doping of your source and drain regions. We'll see why that is the case. And substrate contacts. Okay, and then after that, you put in the connection between metal layers and your sources and drains and your gate, or, you know, an additional metal layers and the connection between those metal layers. So that's when you put in your metal 1, which again is always your lowest level of metal, 2, metal last, which is your last layer of metal. And this is usually, you know, it says M1 and ML. The reason they do that is because you want to make sure everybody's saying the same thing, no matter what process you're in. The metal layer that's the closest to silicon is called metal 1 or M1, okay? Now, different processes can have different number of metal layers between metal 1 and metal last. It might be in a 4-layer metal process, in which case you'll only have metal 2 and metal 3, or you might have an 8-layer metal process, which you'll have metal 2 to, you know, I don't know, whatever, metal 7 or whatever it is. But just so to keep things clear, they always call the first one metal 1, the last one ML. Okay, so you're putting all those metal lines in, then the connections between the metals are called vias, like I mentioned. And so those also go from via 1 to via last. Then you have the contacts and so on. So this is from a very high level of looking at the process. Okay, so this talks about patterning. Okay, so it keeps talking about patterning, because when you're depositing something on the silicon, you're depositing it the same everywhere. The machine is, once it's doing doping, deposition, it's doing the same thing to the whole wafer. Okay, but we know that we actually like different parts of this wafer to be different, because, you know, depending on whether we have an NMOS transistor or P-type transistor, or whether we have a metal of a certain shape on one side or another, like those are all that, this is what makes our design, right? So it's not just one uniform pieces of N plus or P plus or metal 1 or metal 2 or something like that. So you go through this deposition or doping process, and then you go through a patterning. So where you're actually adjusting the shapes. Now, the only control you have is adjusting the shape of the thing sort of from the top. When you look at the wafer, again, from the top, or the silicon chip from the top, you can adjust those dimensions. Okay, so if I'm like looking at a piece of metal from the top, it'll look like this, say, right? I can maybe make it wider, I can make it longer. But in a CMOS process, I cannot change its thickness. That's set by the process. Okay, so all I can do is play with the geometry in the planes of this sort of the silicon. So I can make the width and length of a metal layer wider or longer, pretty much as, you know, there's some design rules which we'll see, but kind of like what I want, but I cannot adjust the thickness. They will not let you do that. You cannot adjust you can adjust how big this drain region is going to be, or the source region is going to be, what this gate's going to be, but you cannot adjust the doping concentration. That's set by the process. You cannot adjust how deep this doping will go. That's set by the process. You can adjust where this contact will go. You can put it wherever you want within the design rules, but you cannot modify the shape of that contact or how thick it is or anything like that. So all of you're basically, what you're giving the foundry is these drawings, but they're all only geometry you can modify as kind of in a two-dimensional geometry for each layer. Okay. Any questions about that? That's, you know, by the way, guys, I think just as an aside, the last couple of semesters we've been kind of screwed because of various reasons. We don't, you know, once we're not on campus, we don't have access to these computer-aided design tools. And those are, you know, very important for doing VLSI design. Like I mentioned, Dr. Olson, myself, we're trying to somehow get those moved into a way where you can have access to them from off campus, but you know, there's all these issues we're trying to sort out. I don't know if it's going to happen. You know, I can't say I'm optimistic. So without those computer-aided design tools, it's especially hard. You know, the part that's really hard to visualize is this physical implementation of these layers. So, you know, we can kind of draw these drawings all we want, but besides doing using the computer-aided design tools, it's a little hard to visualize. So I apologize. So anyway, because of that, you know, some of what I'm saying, it makes it hard to understand, but you know, it is what it is. So anyway, so we're doing this patterning of these, you know, masks. We're doing these patterns. I'm just not saying not mask at the moment, but so how does that patterning work? That patterning works with a process called photolithography. Okay, so the way photolithography works is let's say I want to put a pattern. I want to shape my metal one in a specific pattern that represents a certain connectivity I want. Okay, so the first step is let me just first describe it and then we'll again step through this. So the first thing you do is you spin on a material called photoresist. It just feels like, I don't know what it would be like. It's sort of like, it's sort of gooey, liquidy material that actually gets spun on the wafer. It's very soft at this point, okay? It's called photoresist because if you illuminate it with the specific wavelengths, the part that gets the light gets hard. So instead of being the soft, gooey, watery material, it actually gets stiff. Only the parts that get exposed to the light. It's also possible for it to be an opposite polarity so that when the light hits, it actually gets softer. But anyway, just it's easier to think of it as one way. When it gets hit with the light, it gets harder, okay? And then we can wash away then with a certain process, right? We can wash away the parts that are still watery and that will leave only the hardened patterns that were exposed with the light. Okay, then we can go and etch, use a material that etches metal 1. In that way, wherever there's that hardened photoresist is protecting the aluminum layer, and so that aluminum layer stays on your silicon wafer. Wherever that photoresist got washed away, there's nothing to protect the aluminum layer from that aluminum etchant, and that aluminum goes away. So in that way, you can basically create patterns, or the manufacturing plant can create patterns of aluminum or all these layers we're talking about. Incidentally, that's why, if you guys remember, the lady in the video was mentioning that the lights are yellow in the factory, and all around the world, any fabrication facility, whether it's in the university or, you know, the most expensive, you know, TSMC fab, the lights are always yellow, and that's because they want to make sure that they are not developing this photoresist accidentally, okay? Because the stuff gets spun on and on one location moves to another, et cetera. So that's why there was that yellow light, which gets kind of annoying after a couple of minutes in the fab, or a couple of hours, but can be helped. That's part of the penalty of working in a fab. Okay, so let's sort of walk with that info. So I'm going to kind of say the same thing now with the help of this with this chart, which talks about a particular step in the process. Okay, so if we were just going to look at the process of, let's say we were talking about this, you know, creating these oxide sort of barriers or isolation layers. Okay, so this is done at like sort of the very first step almost. And what you do is, like I mentioned, the same thing happens to everything on the wafer. So actually what happens is, so imagine at this point, none of the stuff's here. You just have the silicon. Okay, so you have the silicon, and the first thing you do is you deposit this thick oxide everywhere. Okay, so what you want to happen again is you have, this is one of the first steps. We're just gonna look at that first step and see how it revs. So you have silicon, and the first thing you do is you deposit, oops, that wasn't a particularly good color, deposit oxide everywhere. Okay. And then what you'd like to do is to, like I mentioned, you wanted to sort of protect some areas of this with that's about same color almost. Let's pick green. So then you want to protect, so this is the photoresist. So I want to protect some parts of this oxide. Okay. And then I'm going to come in and I'm going to etch. I'm going to come in and with something that etches silicon dioxide, I want to get rid of these areas. So after I do that, I end up with this, and this stuff goes away. Okay, and now I'm ready to move on to the next step and put the source drains of my transistors here. So that's kind of like how it flows. So in this particular case, which is this oxide process, the first step is oxidation. So you're depositing oxide on your whole wafer, okay, thick oxide. Next step is you put this photoresist material all over your wafer. So this photoresist it's not exposed yet. So it's still very soft. You can wash it away or whatever at that point, okay? Then separately, the fabrication facility has taken your pattern that you chose for the oxide. You sort of drew that pattern in your computer-aided design tool, gave it to the foundry. They created a mask with that. What is that mask? It's a piece of glass, okay, with wherever you drew stuff, it has chrome. I don't know what the symbol for chrome is. Let's just call it CR. It has sort of chrome areas where you drew your patterns, and the rest of it is just glass. So it's a mask. If you shine light through that mask onto the photoresist, the places that have the chrome won't get any light, and the places that have glass just get the light. So basically what you're doing is you are exposing the photoresist. So through that mask, you're illuminating through that mask, and you're, you know, making that photoresist harder. Okay. By the way, and then also there's this process. I don't know if you guys remember, the Intel video had this thing sort of shooting light and moving around. It basically is doing this process called step and repeat. It's only exposing a part of the wafer, which is one die typically, and then physically moving to the next die, next die, next die, next die. The reason it's doing this step and repeat process as opposed to doing this photolithography process on the whole wafer at a time is because this optics is so precise that you don't want to create a giant lens. I mean, they already have giant lenses, but that, you know, that works across a huge area. You want it to actually, you're trying to optimize it for a small area, and then actually move the wafer, and, you know, so exposing, doing this step and repeat process. So I'm just making it sound like, oh yeah, just shine light through this mask, blah, blah, blah. But the piece of the photolithography equipment, I hope I spelled that right, I don't know, but is the most, by far, most expensive piece of equipment in the fab, by far. It kind of looks like a, what size is it? You guys know those, like those, what are they called? Something pods that people, you know, people want to move. They get that to put in your front yard, and you put all your stuff in there, and at some point they come and take it away. So I don't know, what is that? Like maybe a 10-foot by 10-foot by 20-foot box. It's that big, this piece of lithography. And it's like giant lenses, just amazing optics. There's only really 2 companies that make those. As far as I know, maybe I'm wrong, but Zeiss in Germany and ASML, which I'm not sure where they are, they make those, and they make only a finite number. It's a very complicated piece of equipment and extremely expensive. Might be hundreds of $1 million, okay? And so that's what's used to do this lithography. By the way, just on an aside, and sort of a little bit of a, it's an urban myth, I don't know if it's true or not, but these 2 companies, this is it. These are people who make lithography equipment. So if you want to build a fab line, you got to buy it from these guys. And they only make, you know, I don't know, like 500 a year each or something. So there was this rumor a couple of years back that Samsung was like screwing with TSMC, or I forgot who they were supposedly screwing around with. So supposedly they went and bought like all 500 to stop the other guys from, I mean, it cost them an arm and a leg, but to stop the other guys, sold the other guys from building their own fabrication facility. Is it true? I don't know, but it sort of gives you an idea of like this photolithography step is the most precise, most expensive. This is like usually the bottleneck in the fab of like, because you only have usually any fab line might only have one or two of these machines because they're so expensive. Okay, so at that point you have exposed your photoresist. Okay, then you go through sort of a temperature step to harden it. Then you etch away the photoresist. Okay, and then you basically do whatever etch, assuming, you know, I mentioned etch, but it could be whatever process step you're doing. For example, this would be the etch. And then after you've done your etch, you got to remove. So now you're at this step, you've done the etch, you've gotten rid of these oxide. Now you want to, the photoresist was only there to help you pattern the oxide. You don't want it permanently there. So then you want to go through and you remove this photoresist from this process called ashing, but it's photoresist removal. And then the whole thing starts over again with the next layer. So it's do your deposition across the whole wafer, then you spin on, or you put on your photoresist, you pattern the photoresist using photolithography, then you do your etching or implant or whatever the heck you're going to do, and then you remove the residual photoresist and you repeat. And in a modern process, that might happen like 150, 200 times, maybe more, before you get your wafer. So you get, this is like constantly, these steps are happening, and it's like hundreds of steps, hundreds of times where this thing is happening. Okay. So is there anything you want to say? Yeah, so let's talk about sort of a typical type of thing, process. So let's say you have a 65 nanometer process, say. They're all a little bit different, but sort of the one that I used recently, okay? That had 50 mask layers that we drew. As designers, we drew 50 layers, 50 distinct layers, and we paid for 50 of these masks. Okay, so that had, I think, about, let's just call it 200 steps, because the masks, sometimes they use them, because the masks are extremely expensive. Because you can imagine these are all fine lines in this chrome glass, etc. And it has to be defect free and so on. Otherwise, all the defects that's in your mask will show up on all your die, and not good. So it has like 200 steps. So anyway, was the reason I was going with that is that they try to be creative with the masks. So with the same mask, depending on the photoresist being positive or negative and whatever, they'll try to reuse the mask to do different things 2 or 3 times if they can. Okay. So this had, what they told us was that there is, what was it? In production, it's 6 days per mask layer. Because remember, again, all these wafers are moving around. Sometimes they're getting held up at the lithography machine. So it's not that it takes 6 days to do, a few of these processes. It's just that it has so much wafers running through this thing, waiting for machines, etc., that when you're a customer and they're sort of timing it to keep the fab busy and running efficiently, it might take 6 days per mask layer. Or in this case, which was a very long process, which could take you 300 days before you get your wafers, which is a very long time. That's almost a whole freaking year. Okay, so common numbers are basically between 1 and 6 days per mask layer. So it could take you, so, you know, if things are running fast through a fab, you might get your chips back, you know, from the time you give your database to the foundry, you might get your chips back in 2-3 months. Sometimes when their first favorite customer, I don't know if you're an Apple or somebody, they might do it for you in 3 or 4 weeks. Because, you know, it's not that this is actually how long it takes to etch something. It's more a matter of them sort of organizing their fab lines to get efficient production. So they can go a lot faster. But good, you know, normally it might take you 3 months. It could take to as much as 6 months, 8 months, 9 months. But so that's from the time you send your design to the factory to get wafers back. Okay. What else do I want to say about this? I think that was it. So, all right. So now, so this is sort of like this photolithography process that happens over and over and over and over again, and, you know, might happen 150 times. Okay. So now let's look at the entire process. Now that you know photolithography, etc., let's see what. Let's walk through a process. Okay, so we said we start with a P+ wafer. Okay, so the first thing they do is they grow epitaxial layers on top. So P+, again, you want it for low substrate resistance, for good grounding. And the P-epi is just so that you can adjust transistor thresholds and so on. So that's why you grow it. So the next step is you grow a silicon dioxide layer, thin silicon dioxide layer. Then you put a silicon, this is getting pretty specific, but just sort of like follow the fact that in this case, they're using the silicon nitride as a mask for silicon dioxide. Okay, so this is for the building the trenches and the isolation. Okay, the reason they're using silicon nitride here for a mask is that sometimes when a process step is very intense, is very damaging, this photoresist material isn't just through photolithography, it doesn't get hard enough to resist something that's too intense. Okay, so a process of deeply etching silicon, so this is doing the silicon etch, is this process called reactive ion etching, but it doesn't matter to you guys. But it's like, let's just say it's very, very intense, very damaging. So what they've done here specifically is they've actually first patterned silicon nitride, which itself is harder than photoresist. And all they've used it for is as a mask. So they patterned the silicon nitride and used this as a mask to etch through the silicon. Okay. So after that step, what they did was they removed this nitride layer is just a mask. So you want to remove that. Okay, and you basically fill those trenches, you fill these things with oxide. Okay, so they go deep into your silicon, by deep, maybe 3, 5, 6 micron deep into your silicon, and to be isolation for your transistors. So you sort of put your transistors in between these trenches that you dug and filled for isolation. Okay, so after that, basically what you do is you cover where you want your N MOSFETs, okay? And you implant your N well for your PMOS, and you put in what's called the threshold voltage adjustment for your PMOS transistors, because if you just build a PMOS transistor's threshold is going to be too low. You want to increase it a bit. So you put an extra implant to adjust that, okay? Next, you cover your PMOS areas and do the same with your N well. So N transistors. So you cover your Ps, and then you put your threshold implants for the N transistors, okay? So at this point, you're just created, what have you created? You've created your isolation, you've created your N well for your PMOS, and you've doped the channels for the N and the P, so when you get the transistor, it'll have a reasonable threshold voltage. Okay, next step is you deposit your polysilicon. These are the gates for so this is the gate for the NMOS, gate for the PMOS, okay, and you etch that down to pattern it. Okay, so this is an important thing. So this was a big breakthrough many years ago. It's called a self-aligned process. So when we drew the cross section for a NMOS transistor, say, so this was the dielectric, this was the poly, this is the, N plus, this is the N plus source and drains, right? So we drew them like these things line up precisely, right? But there's nothing that says, if you just did it mask after mask, there's nothing that says it, there's some mismatch between the masks. However precise it is, there's no guarantee that things, as you'll see, will, there's always some nanometer shift. There's just some slop, even in the most precise process, okay? So it could easily end up being, so this is kind of like good. You could easily end up in a situation where you screwed things up and this is your poly, you end up, actually stuff moved over a bit. So now you have a gap between, say, source and the drain and your gate. So this is like a extremely unfortunate situation, because it means your transistor isn't going to turn on. So because there's no channel here. The gate can't put a channel there. So what they did was they said, okay, how can we make this perfect every time? How, regardless of alignment, manufacturing tolerances, whatever, how can we line this up? And then I don't know who was the genius that came up with this, came up with the self-aligned process, which is that you actually dope the N plus and the P plus sources and drains using the polysilicon as the mask. Okay, so that's why you deposit the polysilicon first, and then you basically do ion implant on this whole thing. This guy stops the ions from going here, the polysilicon gate, and wherever it's not, you get N plus. So basically your sources and drains become self-aligned with the poly, regardless of alignment accuracy. So that's why you have it. You do your N source drain implants after you do your polysilicon gate deposition. Okay. So the next step after that is now you're sort of done with everything to do again in underneath the silicon surface. The only thing that you did over the silicon surface, I guess, was the polysilicon. And now you start putting in stuff for your metal layers. So you start putting in this oxide layer as your dielectric. So when you put your metal, it won't short to your gates except where you want it to. Okay, so that's the first step, is this silicon dioxide deposition. And after that, you put your, this is metal 1, first layer of aluminum or copper. Copper is slightly different, so this is describing aluminum, but similar. So, and then you etch where the metal 1 is. Okay, then you put another oxide layer between metal 1 and metal 2, and then you deposit your metal 2. And previous to that, you have also defined where metal 2 connects to metal 1, which is also etched in. And then that gets deposited, and then you sort of built all your metal layers, and then you are done. Okay, so that's kind of like this step-by-step process. First, you build up your transistors, and then you start building up everything on top of that. Now, this is like probably very, very difficult to follow, but I hope it gave you guys an idea. Okay, so I don't know, for whatever it's worth, this is a 3D perspective of and MOS transistors is kind of what you might end up with. Okay, so how does this look when you, as a designer, are designing these masks for the foundry? So you never are seeing things unless something bad happened. You actually never are looking at or touching this cross section when you're doing design, because you have no control over these thicknesses. I mean, it's just important for you to know what's going on, but you can't adjust anything here. You can just adjust these shapes, okay? Not in the Z direction out of the wafer, but in the X and Y direction with the wafer. So whenever you're doing the design of these masks, is as if you're looking down on the wafer. So this is all like a top view. And if you did a cross section, if you cut a line across this, you'll end up with seeing this cross section. But when you're actually designing, you end up with this top view. Okay, so what does that look like? So basically what you're doing is you are, okay. So you are making, this is like, trust me for a second here, this is your polysilicon gate. This black thing here is the contact to your polysilicon gate. And you can make this wider, you can make it longer or narrower, whatever. And that's what you have control over. You can decide where you drop this contact, so on and so forth. Okay, so let's see where it looks like if you're going to make a transistor. Well, first thing is you need to define where your end well is. Wherever there's an end well is the PMOS transistors, okay? So you'll have in your computer-aided design tool or mask layer, so you'll just have a rectangular drawing where the PMOS transistors are going to be, okay? Next thing you do is you want to define where your sources, drains, and substrate contacts are going to be. And there's this layer called active, okay, which defines that. It's always called active. Okay, so these are, like, for example, so by the way, when I superimpose all these guys on top of each other, I get this. Okay, so like if I'm looking at this here, here's this well, which is this guy here. Okay, here are the actives, which were drawn here. Here's the polysilicon. So each one makes its own mask, and you as a designer are drawing each one separately. You're seeing them on your screen superimposed on each other, but at every step, you're only just touching one mask. You can go back and forth between masks, but when you're drawing masks, you're only drawing an individual layer, okay? And here are the contacts. So you see that here's the contacts in this mask layer, and same with the metals, metal. Okay, and when all these guys are superimposed, they make, this looks like an NMOS transistor, and this is a PMOS transistor. Okay, so like I mentioned, the polys are the gates. Wherever there is an overlap, so overlap of polysilicon, silicon, and active defines gate. So for example, here is polysilicon, here's active, here's the overlap, where they overlap. That's the gate of the transistor. Remember, this area gets implanted, this area gets implanted with N+, but there's no implant with N+ here because the polysilicon itself is acting as the mask. So this is your gate. So this is again active for the PMOS, and this is the polysilicon for the PMOS, and that becomes the gate. Okay. Okay, guys, I think I'm gonna stop there because we're gonna talk about design rules, and that's, I think this is a good stopping point for thinking what. So what I wanted you guys to take away from this lecture was that the CMOS silicon wafer is a planar process. Okay, so you're always thinking about the whole plane at the same time. So there's the transistors are all in the same plane. You're doing the processing as if you're playing with one plane at a time, and that the processing are like a series of steps on each individual plane. And as you pattern those different layers or implants, etc., you're sort of building up your chip. And you have no control in the z-axis, all like, how thick anything is, doping concentrations, you have zero control over any of that. The factory's already developed that particular process and has told you that's the process. The only control you have is over the geometry of these layers in the X and Y direction, which is in the plane of the silicon wafer. Okay, guys, any questions? No?
No.
Okay, guys. Well, I know this is kind of hard to absorb, but hopefully between the videos and the slides, etc., it kind of gives you an idea. Anyway, so I was hoping that I was going to have the lab for you guys today, but I guess it's going to be by sometime this weekend. I'll put it up, and then we'll talk about it on Tuesday, and I don't know, we'll have to figure out a good due date for it. So like I mentioned, we do not have access to the CAD tools. So, all we can do in our labs is circuit simulation, which is like a big part of the design. So, and then we're going to use basically Splice to do simulations. I personally use something called LT Spice. It's something that runs on both Macs and PCs. It's freeware. There's no limit to the number of transistors. It's from a company called Analog Devices. It doesn't have the best user interface in the world and stuff, but does everything as far as I can tell. So I use that. You guys can use, I know PSpice is popular for you guys. you can use that if you like. You're not limited to use LT Spice. But the only problem is, I only have a Mac. I only have LT Spice. So if you run into problems with your PSpice, I can try to help you, but I can't like simulate it on my computer to help debug. If you give me an LT Spice schematic, you're stuck on something, at least I can, poke and prod here and there, see if we can solve it together here remotely. So my advice is to use LT Spice. If you're familiar with PSpice, you're just as welcome to use PSpice, and it's up to you. And I saw Logan's note to the class that HSpice is better. It is better. HSpice is a much better, more accurate engine than is available either in LT Spice or PSpice. And in fact, there's other engines that do the math behind the simulations. Cadence has sort of the chip design tool. It's called Spectra, which is, competes with HSpice. There's another, Mentor has another tool called AMS that competes with its own HSpice and with Spectra. Those are better tools than what we have access to. But for this class, we're not talking about large number of transistors, and we're not talking about analog design. So I think either LT Spice or PSpice is going to suffice. If you guys want to use something else, you're welcome to some other flavor of Spice that can simulate transistors. But anyway, I recommend LT Spice just so I can help debug with you guys, debug your stuff. And so I have a tutorial for LT Spice that's on YouTube. And then I have some example files with this particular process that you're going to be working with. So I'm going to put those on Blackboard. So if you guys want to use LT Spice, you can sort of use those as a starting point for this process. I will also, there's some Spice decks for this process, which you'll find. So if you want to use a PSpice process or something like that, you're going to have to import those into PSpice. I don't think it's that big of a deal if you're used to using PSpice, but so just to make sure you're starting with the right simulation sort of transistor deck. Okay, guys, if there aren't any questions, I'll let you guys go and have a great weekend.
You too.
Thanks. Bye.